Next speaker is Professor Gianni Royer-Carfagni. He will talk about the high-performance windows for applications in space, open problems and challenges. Professor Carfagni is Professor of Structural Mechanics at the University of Parma. He's also CNR Research Associate, Adjunct Professor, University of Houston, and he has visiting roles at leading global universities. He's also a member of several committees, standard committees, and he's also chair of the Structural Glass subcommittee. He's vice president at Italian Glass Technologies Association, and he's also founder and president of Space Glass. So if you're ready, Professor Carfagni, the stage is yours.
Thank you. Thank you. I'm talking about Windows for space application. There is also this application. Here is a review. We start for the project Mercury. I tried to emphasize the Windows. The project Mercury in 1958, then the Gemini 1961, the Apollo 11 that brought the first man to the moon. 1969, the space shuttle started in 1985. Now, more recently, the Dragon capsule by SpaceX, 2022, and the ongoing project with NASA, which is the Orion spacecraft. There are some ongoing projects, specifically for space application. One is this cupola, to be installed a Space Dragon Dome Observatory. You can see the size of this cupola here mentioned. As a matter of fact, SpaceX is very protective, so I don't know very much about this project, but I know quite a little about this. This is the observatory. It's, you can see there, it is a completely glazed structure. Here on the bottom side, here you can find the new design for this. And this has been designed by Philip Stark, together with Mike Suffredini, who was the manager for the International Space Station at NASA before going to Axiom Space and founding Axiom Space. You can see the size of this observatory. Probably it is planned to be installed in 2030. The problem on space station is slightly different from that of the spacecraft, because the space station is to be there for several years. The state of the art of glass glazing probably represented by the International Space Station cupola, or cupola, as they say in the United States. You can see that it is formed by 6 trapezoidal windows and one central window, which is 800 millimeter in diameter, which represents the greatest windows ever made for space application. Then you can see that there are these shutters to protect the window when it is not in use. By the way, the trapezoidal windows were borrowed by the space shuttle. And this was the frame, which is a single forged aluminum frame, 18 kilonewton in weight. It was made in Italy by Alenia, and the whole cupola was assembled in Italy by Alenia, now Thales Alenia Space Italia. So a brief review, apart from what I have already mentioned. This is a cross-section of the window of a space station. You can identify 3 subsections: a debris pane on the outside to protect from space debris, 2 pressure panes, which are depends on the size of the windows, but the thickest one are each one 36.8 8 millimeter. And the two pressure pane, the second one is added for redundancy, and an inner scratch pane that is used to protect the pressure panes from accidental damage from the inside. There is a gap between the pane, the pressure pane. It is ventilated to the outside. So only the inner pane is pressurized, the other does not bear any load. You can see here from the interior that there are these little tubes that connect the outside to the vented gap. And there was a story about that because the astronaut some years ago were handling them. You know that there is no apparent gravity in the International Space Station. So they broke the pipes and there was a pressure drop inside the whole International Space Station. The paints are all made of fused silica. Recently, to protect against radiation, the inner scratch pane was replaced in acrylic. And it is designed, this design allows for replacing the paints. Of course, you need extra vehicle activity, so it is not so easy, but must be designed to be replaced. And it is the whole cupola is designed to stay in orbit for 10 years. Even if it was installed in 2010, but the International Space Station will probably be dismissed in a few years. So there are many hazards because designing windows for space application is not as easy as for terrestrial application. There are material outgassing. You have to take into account debris impact. There is the electromagnetic radiation from the sun on the Earth that it is not shielded by the atmospheric pressure on Earth. Then atomic oxygen interaction with material which may produce the degradation. The effect of protons, electrons, which are trapped in the Van Allen belts and can attack the material. Gamma rays that are either produced by the solar radiation or may be produced by the impact of electrons on the material. And then also neutrons produced by cosmic rays. And transparent material pose a unique challenge because they must reach a compromise between optical clarity and radiation shielding effectiveness. And for example, now the design, the scenario that is usually taken into account is not that of the International Space Station, but it is the one which corresponds to a little higher orbit, a sun-synchronous orbit at 550 kilometer height within the low Earthian region, which is partially measured in the Van Allen belts and also passes through the South Atlantic anomaly where there is an environment at a lower altitude which is very similar to that caused by the Van Allen belts. Which are the most used materials? Fused silica is the one that has been traditionally used, but in recent years also acrylic glass is being used for phase penetration, and we are presently working very much with acrylic glass. And must say that there is also a story about that because during the disaster of the Space Shuttle Columbia, I guess it was 2003, the only sound piece that came back to Earth was a windows made of acrylic glass. From that, NASA has become confident that acrylic glass should be the material for the future. these are just a comparison of the various materials. You can see that, yes, acrylic glass has a lower density. I'm just highlighting fused silica and acrylic glass properties. But you can see that whereas the bending strength is comparable, the Young's modulus is much lower. And also the Achilles heel of acrylic glass is the operating temperature, because the glass transition temperature for acrylic glass, which is a PMMA, is about 100 degrees Celsius. And also the coefficient of thermal expansion is quite high compared with that, of course, of fused silica, which has almost a zero coefficient of thermal expansion. There are, however, some drawbacks for fused silica and aluminum frame. First of all, the bending strength is not so high. The fracture toughness of fused silica is not so high. It is true that there is a very low coefficient of thermal expansion, so that an uneven temperature distribution does not cause any big thermal stress inside the material, but there is a thermal mismatch between the aluminum frame and the fused silica. This stresses the gaskets. You know that everything should be airtight, and consequently the gaskets are very important elements in the window design. Then there is a difficulty in manufacturing very large windows made of fused silica. It is very expensive, and most of all, fused silica does not have a static fatigue limit. This means that in theory, even if this time could be very long, fused silica, whatever the applied load, there is a time at which the material will fail because of slow crack propagation in that. We take into account this also in ordinary glass, but for fused silica is a very important issue. Also, if you take into account the mechanical capacity, well, the problem of acrylic glass compared with fused silica is the low elastic modulus. And of course, you know that the stiffness goes to the cubic power of the thickness of the element. So if you want to compare the mechanical capacity in terms of stiffness and strength of fused silica, the acrylic glass, you have to consider different thicknesses. And what is important to know is that sending material to low Earth orbit costs a lot. Although Elon Musk says that he will send 1 kilogram to the orbit for $2,000, now the average price is $20,000 per kilogram. Sending 1 kilogram to the moon, the actual price is $1 million per kilogram. So you can see that even saving 1 kilogram in the window is a very high cost saving. For example, if you consider the pane that has been used for the International Space Station, you can see that the launching cost is about $1.6 million per square meter. If you use acrylic glass, it is true that the weight is less, but if you want to make a large window, you have to increase the thickness to have the same stiffness. And so the price is about double that of a fused silica pane. So you have to be a little bit careful about that. Now, I don't have the time, of course, to tell you a lot of things about all the peculiarities that I listed before. I'm just presenting an example about electromagnetic waves, the effect of electromagnetic waves in low Earth orbit condition. First of all, what are the main radiation sources? It is the sun, the radiation from the sun, the radiation from the Earth albedo, which means the radiation which is reflected by the Earth. Then the Earth planetary radiation, which emits radiation like a black body. And you have very variable conditions which are connected to the angle that the orbit makes with elliptic plane. In the International Space Station, the ISS makes a revolution every 90 minutes, so very variable condition. What we have added is a model of an orbiting box in which you have various phases, because the windows can be oriented in various ways with respect to the incoming radiation. This is the electromagnetic radiation due to the sun and the Earth albedo. Here the spectrum, this is the spectrum, and the range of visible light is evidenced, whereas for the Earth planetary radiation, basically the emission is in infrared range. And you can see that there are various scenarios. For example, the beta is equal to 0 corresponds to the greatest variation. But if you want to find out what is the condition, the worst condition for the glass, so when you have the greatest radiation, you have to consider beta is equal to 75, which is more or less the upper bound, in which some of the windows are constantly subjected to solar radiation. So for what concerns the absorption, reflectivity, transmissibility, and absorption, the property of each material depends on the wavelengths. So you have to consider now, it is very important to consider the response on any wavelength of a spectrum and then integrate all the contribution. As you can see here, we have various responses at various wavelengths. So if you know the spectrum, you can find out what is the average properties to make the calculation. For what concerns the solar spectrum, acrylic glass, there are many types of acrylic glass, so it's also difficult to talk about acrylic glass, because there are so many types, and each one, the data that you can find are sometimes incomplete and also contradictory. But anyway, for what concerns the solar spectrum, fused silica in practice does not absorb anything. It's completely transparent in the whole range of the spectrum, whereas acrylic glass has some absorbance, and this is also a reason why it is used, because it can protect the astronauts from the radiation. For what concerns instead the infrared planetary radiation, both materials are almost, they do not transmit anything. The infrared radiation remains limited and bounded in a very thin layer, both for fused silica and for acrylic glass. So I just present you an example in which I consider the same package of the International Space Station. You can see that you have an energy distribution that varies a little bit depending on the wavelength because of the limited absorption of fused silica. But since it is almost transparent, you don't have a very strong dependence of the thickness, because it is transparent more or less, so the dependence of the properties of the windows are only mildly affected by the thickness. And the temperature that you can reach during the transient state for both beta is equal to 0 and beta is equal to 75, which are two borderline cases. You can see that on the various pane, in the internal pane are dictated by the internal temperature. On the outer pane, they are dictated by the radiation with the deep space, so they are very low temperature. And of course, in vacuum, there is no convective heat exchange. Now we made an exercise. Since acrylic glass is being used, what would be the difference if you substitute one of the paints with acrylic glass? Of course, you have to consider very thick acrylic glass in order to have the same thickness of fused silica. And what you can see now is that the acrylic glass takes most part of the radiation, because it is the only material that absorbs. There is also a heat exchange between the paints due to the radiation of acrylic glass on fused silica. And the temperature, you can see that now the period of 90 minutes of revolution comes into play, because you can see this kind of responses, this wavy responsive. And an important thing is that there are conditions, in particular the angle beta with respect to the orbit with respect to the sun rays, 75 for a left-facing pane. In theory, you could reach 200 degrees, almost 200 degrees in the acrylic glass pane. And this means that, of course, you are close to the glass transition temperature, so you cannot use it anymore. So I would like to summarize our contribution. Well, this is an unusual application, but most of the times innovation has come in the aerospace sector, and then a downgrade of the technology has been used in other types of application. In particular, what we are learning from this are the property of acrylic glass in these very hazardous conditions. And of course, we think that we are also doing some other things, for example, using lamination with silicons, but I'm not talking about that, in order to try to obtain high-performance windows at a reasonable mass, because everything must be optimized for cost reasons. So thank you very much.